and then a summary at the end. Okay. All right, so this is this compare the SDV with LDV, but when we do not learn the SDV in this course, so I will I will skip this slide. But so this is a comparison between the SDV and LDV, right? So I'll skip this slide and then we can come back later if there's any question about this. Okay, right. So AODV is on demand as well, just like the SR are reactive in the sense that we don't build routes in advance like on the internet. We only build routes or we establish a route when we need to send data, just like the SR. It uses bidirectional links. So that means the links must be bidirectional. It has to work both ways. It has a route discovery process, just like the SR. Okay, and it maintains active routes. Okay, so the SR does not really maintain active routes. It just caches the routes, and those routes may be obsolete, maybe stale, right? AODV actively maintains routes, and it uses sequence numbers to prevent loop and to make sure that routes are fresh, up to date. Okay, so we'll learn about sequence number later. So sequence number are used to prevent loops and to make sure that routes are up to date. And it provides both unicast and multicast communication. So we will not talk about multicast. We will only consider AODV for unicast for now, okay, to simplify the lecture. Okay. So with AODV, as we said before, it maintains only active routes. So when routes are not used, after a while, they expired. And when they expire, they will be discarded. Okay. So by doing that, AODV reduces reduces the number of obsolete routes. And it also minimizes the amount of work needed for route maintenance. Okay? And it also minimizes the number of active routes between a source and destination by letting routes to expire and then throw away those routes. AODV, when it uses the route discovery process, just like the SR, it can discover multiple routes between a source and destination, right? And remember with the SR, we can have several routes between a source and destination, but we keep only one. The same with AODV. After the route discovery process, there may be multiple routes between a source and destination, but AODV keeps only a single route. In order to simplify the implementation, to simplify route maintenance, okay? Because it would be difficult to manage many routes. A lot of bookkeeping has to be involved to keep track of many routes. And if one route breaks, it's not easy to know whether the other routes are still good or not, up to date or not, right? So to make things simple, even though AODV can find many routes, it keeps and uses only one, just like the SR. Okay. So just like the SR, AODV discovers routes only when necessary, all right? Only when it needs to send data from a source or destination. And by the same principle, routes are maintained or kept as long as necessary. That means after a while, if a route is not used for some amount of time, a timer expires, and then that route is thrown away, discarded, okay? And every node maintains monotonically increasing sequence numbers. And the sequence number are increased every time the node notices change in the neighborhood topology. Okay. Now, the concept of sequence numbers are very important in AODV. But this name here, sequence numbers, the name, the terminology is very misleading and confusing. So when I learned about AODV, I was a graduate student. And I was a PhD student. And it took me a couple of days to figure out the real purpose of sequence numbers. Because they should not name sequence numbers. So when you heard the term sequence numbers, or at least when I heard it, what I was thinking about is, remember in TCP, every packet has a sequence number, right? Let's say you named you number a packet from 1, 2, 3, 4, 5. And then when you don't receive packet number 4, you know that 4 was lost, right? So basically sequence number is to maintain the order of the packets. But in AODV, the sequence numbers are not really to keep track of packets. They are to keep track of the events, right? So a better name would be event numbers. Okay, a better name could be event numbers. And why do we need event numbers? So I just give you a analogy. All right, so assume that one day you wake up and somehow you find yourself on another planet, not planet Earth, right? And there is nothing there except food and water and everything that you need to survive, but nothing else. No clock, no cell phone, nothing. Just enough food and water for you to survive. Now, without a clock, and assume that the sun is always set, it never goes down. So you have sunlight all the time. So in that sense, how can you keep track of time, right? Because you don't have a watch, you don't have a clock, you don't have your cell phone, you don't have your computer, and the sun is always shines. How do you keep track of time, right? And if you think about it, you don't need to keep track of time because everything you need, you already have it. You have food, you have water, you have a cave to live in, right? You don't need to go to work, then you don't need to keep track of time. But you must need to keep track of the order of events, right? So let's assume one day you wander around the island or the planet and you meet another person. And then you fall in love with the person. And then you plan to marry the person, So you could say the event land on the planet is event 1. And then meet that person is event 2. And get married is event 3. And then after you guys get married, you have the first child. That could be event 4. So, you know, you have these events numbers so that you know which event happens before or after another event. And that's how you keep track of time, right? Because you don't have a clock, you don't have a watch, you don't have anything to keep track of time. The only way is there may be many events and then you name them, you number them with a number so that you can keep track the sequence of events, all right? And that is the meaning of sequence number in AODV. When an event happens, you give a number to that event, okay? And if an event has a higher number than another event, that means it happens later, okay? So that's why you can see here it says increases every time the node notices change in the neighborhood topology. When there's a change, that implies an event happens. So let's say a link is broken, right? So the event number would be increased. So this link is broken at event number 10. And then after a while, another link is broken. So you could name that event as event number 11, all right? So every time you see the term sequence number in these slides, don't think of it as the number of the packet or the message, but think of it as the event number associated with that packet, all right? Okay. So yeah, very important, because if you think about it as the sequence number associated with the packet itself, the sequence number of the packet itself, it would be very confusing. Okay. All right. So so let me see if we should start with the okay, I think we should start with this route discovery. Okay. All right, so AODV route discovery also start by using route request, just as DSR. Okay. So when a node wants to send a data packet to a destination, so it will check the routing table, right? So remember, with the DSR, we don't have routing table. With AODV, we have routing tables. The source checks the routing table to determine if it has a route to the destination. If yes, then it sends the packet to the next hop node, right? We'll talk about this later. If no, there's no route, then it will initiate a route discovery process, just like with DSR. Okay. So again, just like DSR, it will create a route request. Okay. And the route request contains the following information: the source address or IP address, all right? The source current sequence number, okay? So now remember, as I said before, this sequence number, basically an event number. So creating this route request is an event. So what is the number of this event? Okay, it's not the sequence number of the packet. It's the number of this event, and the event is create a route request, okay? And then the destination address and the destination sequence number. Again, the destination, it has that the destination has its own sequence of events, right? And because of that, it has its own event numbers as well, okay? All right. So remember, each node has its own sequence of events. So let's say when a node create a route request, it has its own events. That's considered as an event. When it sends another route request, that could be another event, for example. All right. And because different nodes perform different kinds of activities, operations, so they could have different sequence of events. So they maintain their own event numbers or sequence numbers. Okay. All right. So, and each packet also contains a broadcast ID number. And the broadcast ID gets incremented each time a source node uses route request. Okay. So the broadcast ID and the source IP address form a unique identifier for the route request. And the reason for this is so that when a node receives a duplicate route request, right? When a node receives a route request, it would record the broadcast ID and source IP address. When it receives a duplicate route request, it will check and it knows that it saw the broadcast ID and the source IP address before, so it just throws away the duplicate route request, okay? And this combination helps to minimize the number of duplicate route requests forwarded to the neighbors, right? So that's the reason for this. And broadcasting is done using flooding. Yeah, just like in DSR, we flood the network with route requests, okay? All right, so flooding, the concept of flooding, we already saw this in DSR, okay? So these slides are about the principle of flooding, okay? So I will skip these because we already saw this before in DSR. Now we go into specific of AODV, okay? All right, yes, this is related to specific to AODV, right? So, okay. All right. So let's see, should we go through this or should we consider one example first? Okay, so we can consider this quickly. We'll go through this quickly and then we consider one example to make it easier to understand. So we said before, when AODV wants to send, when a source in AODV wants to send a data packet to the destination, but it doesn't have a, a route to the destination, it will broadcast a route request, okay? And once an intermediate nodes receive a route request, the node set up a reverse route entry for the source node in its route table, okay? So what does that mean by reverse route entry? We will see an example later, okay? And the reverse route entry would have the source IP address, source sequence number, again, or source event number, number pop to the source node, and IP address of the node from which the request was received. Okay, we'll see an example later. So using the reverse route, so when the route request arrives at the destination sends back a route reply, okay, the route reply. And the route reply will use these reverse route entry to go back to the source, okay, to go back to the source. So in the SR, the reverse route is recorded in the route reply, okay? With AODV, we don't record the reverse route in the route reply. We use a reverse route entry at every node, and we will see an example later, okay? And the reverse route entry has a lifetime field. So basically the lifetime field here, it is like a timer. When this timer expires, we delete this entry so that we can free the space for future users. Okay. All right, so okay, so now let's see here. Okay, so let's consider one example first before we go into this next point. Okay, so we'll consider example to illustrate this point first, right? And then we come back to this. I don't want to talk too much about theory without seeing an example first, okay? All right, so this is the example. All right, so assume S want to send data to D. So S needs a route to D, okay? So S will create a route request, and the route request would have the destination, would have the source IP address, right? The event number at the source. And this would have the destination IP address and the event number of the destination. And then the hops count is 0, right? So because right now there's no path to this, so its hop count is 0. Every time a node receives the request, it would increment the hop count to indicate that this is the length of the path from S to that node and eventually to D. Okay. So the hop count is basically the current path length. All right, and then S will broadcast the route request to neighbor. So assume it has all the neighbors here, right? But we just keep only one node, which is A. So S send the route request to all the neighbors. Remember, all neighbors. But now A received the route request. All right, so when A received the route request, A will create a reverse route entry for S, okay? Why we call it reverse? Because now A will make S a destination, okay? Because the source of this message is S, but from A's point of view, in order to send something to S, A had to use this link. So now A is the source. And because if A wants to send something to S, A is the source and S is the destination. Because later A may need to send back the route reply to S, right? And when A sends the route reply back to S, A is the source, S is the destination, right? So that's why we have the term reverse here, because this is the reverse path from S to A, right? This is the backward path from S to A. So that's why we have the term reverse. And that entry will have destination as S, because this is the destination of the route reply. Okay, so A records information for the route reply in the future. So destination is S. The next hop is S. Basically, yeah, the next hop is S in this case. And the hop count is 1. So it increments the hop count in here from 0 to 1. Okay, all right. And A has no routes to D. Okay, so it has no route to D. So that's why it rebroadcasts the route request. Okay, so it rebroadcasts the route request to everyone, just like the SR. Okay, so okay, all right. So I think we've seen this. All right, so now assume the route request arrives at C. Now it also arrives at B as well, right? But we examine the activities at C, the operation at C here. So again, C will create a reverse route entry. All right. So basically, it's a route entry, but we say reverse because this route entry, it will be used for the reply, right, on the way back to S. So that's why we call it reverse. And what is this entry? So basically, the destination is S, right? Because this is where the route reply has to reach. So it put the destination S for the route reply. And the next hop is A. That means C has to forward the reply back to A. So that A can forward the reply to S, right? So that's why next hop is A. And the hop count is 2, right? It increments. It was 1 before, now it increments to 2. Okay. All right. Now, assume in this case, they assume that C has a route to D. Okay, C has a route to D. Right. So just like the SR before, if an intermediate node has a route to the destination, it can send a reply back to the source immediately. Okay, it's what without forwarding the route request. So in this case, it's assumed that C has a route to D. And it has a route to D because in the past, maybe it sent something to D, or in the past, someone has asked C to establish a path to D, for example. Okay. So assume that C has a route to D. Okay. Now, this is important, the second part. The sequence for the route to D, okay, is greater than or equal to the sequence number in the route request. Okay, so assume that the route request has the sequence number 10. Okay, so I'm not sure how to write here, but let's say we have 10 here. Okay, all right. Sorry. Yeah, I'm not sure how to write on PowerPoint. Okay, we did it. So assume S has the destination sequence number in S is 10, right? 10 here. Now, if C has a route to D and the sequence number here is 10, 11, or 12. So what it means is the event to establish the path from C to D happens after the event of this route request. Okay, remember we said event. If a higher number means that event happens after another event with a lower number, right? So if C has a sequence number for this route here, let's say this route from C to D has sequence number 11. That means this event happens after this event at S, after S tried to discover the new path. So that means this route is new, up to date, right? This route is up to date. So in that case, C can send back a route reply to S saying that I have a path to D. Okay, so the route reply now would be to send back to A and then send back to S. Okay, now assume if we don't have this condition, basically the route here has sequence number 5. Okay, the route here has sequence number 5 for D. So, and the route request here has sequence number 10, the event number 10. Event number here is 5. So you can see that means 5 happened a long time before 10. So this route may not be up to date anymore. All right, maybe not up to date anymore. So in that sense, C cannot send back a route reply. Okay, because now this route has event number 5. It's older than the current event. So C should not send back the route reply. Okay. So you can imagine this as you buy a new laptop, a new computer, and this software here has a much older version, much older operating system. You should not install this operating system in your new laptop. All right, it's the same concept. The route here happened a long time ago, so it may be obsolete by now. Okay. All right. So, but in this case, we assume that C has a route to D, and the sequence number for this route is greater than the sequence number or the event number in the route request here. Okay. So in that case, C will send back a route reply to S. Okay. All right. And how does it send back the route reply to S? So in the route reply, the destination would be S. Okay. And then it looks up in its routing table. It says that the next hop is A. So it will forward the route reply to A, right? It will forward the route reply to A. And then when A receives the route reply, A will look up in its reverse routing table. It sees the destination is S, right? So that means the next hop I should send is S. So it send the this back to S. Okay, it send back to S. So now S has the S doesn't have the complete route. It only knows that to send information to D, it just needs to send to A. That's it, because A would be the next node from S. So it doesn't know, S doesn't know the complete route to D. It just knows that in order to send to D, it has to send to A, all right? It knows that the hop count is 3, right? Because C would increment this to 3 in the route reply and send back to S, okay? So that's all it knows, okay? All right, so now in this case, assume that C doesn't have a route to D, okay? Assume C doesn't have a route to D. So in this case, C will broadcast the route request again, okay? Broadcast the route request again. And then D will receive the route request. It knows that it's the destination, right? So it will make a reverse route entry as well. Basically, destination S, next hop would be C, right? Hop count would be 3, right? So D will create that entry, destination S, next hop C, hop count 3, and then D creates a route reply, all right? And put the information in the route reply, destination S, hop count 3, right? And send the route reply to C. And then C receive it, sends to A using the this reverse route entry, right? A receive it, send to S using this reverse route entry, okay? All right. Okay, so now get back here. All right, so now you can see this is what we just talked before. I think this should not be here. I think this is wrong. I think I would say, I wouldn't say rigid destination, I would say on the way to the destination, right? So the request on the way to destination, okay, is on its way to destination. And then so on the way to destination, it arrives at a node, let's say C in the previous example, okay. If C has in its routing table an entry for the destination, basically C has a route to the destination, okay, and the event number for the destination is at least as large as the event number in the route request, okay, we said about that before, to ensure that the route is up to date and to ensure that there will be no loop. Okay, so we'll talk later how loop can be formed if we don't have event number or sequence number. So in this case, C, if it has an entry for the destination, the entry should not have expired, right? It has to be up to date. And the sequence number of the destination or the event number for the destination is at least as large as the event in the route request. Then C can send a route reply back, right? It can send back a route reply, as we said before, using unicasting and not flooding, okay, not flooding, because now it has the reverse path to A, right? C has a path to A and then A to S. All right, now if the conditions are not met, right? So basically these two conditions, if they are not met, not satisfied, then C increments the hop count in the route request, and then C will broadcast the route request to the neighbors. Okay. So I think we should say this. This is not bridges on the way, right? On the way to destination. Yeah. Okay. All right. So and eventually the route request will make its way to the destination, right? And the destination will send back a route reply, as we said before. Okay. Right. So okay, so we'll skip this. Okay, yes. And this is what we said before. An intermediate node, right? C in our previous example can send a route reply if it has a more up-to-date path or recent path or up-to-date, more up-to-date, right? And then to determine whether the path is more up-to-date or more recent or not, we use the destination event numbers, right? So that's why we said before, if the event number is the same or greater than the event number in the route request, then C can send back the route reply. But if the event number is lower than the event number in the route request, that means this path was discovered in the past, and it may not be up to date anymore. Okay, yeah. Okay, so yeah, so it says here, an intermediate node, which node around, but with a smaller sequence number cannot send route reply, right? If it has a smaller destination event number, it cannot send route reply because the path is obsolete compared with the current route request. Okay. Right. So okay. So this is So this is what we said before. If C satisfies the two conditions, it has a route to D that has not expired, and it has a larger destination event number, then it will create a route reply, okay? And it unicasts the route reply to A, send back to A here, okay? Using the reverse route entry in the routing table. And then, yes, send to A, route reply. And when A receives this, it will send back to S, right? And when, remember this, when A receives the route reply, it will create a forward route entry for D to D. Okay, remember this is not reverse, it's forward. Basically, this is how A can send packets to D. All right, so that's why it would say destination is D. All right, destination is D. The next hop is C. Right, next hop is C. And the hop count is 2. From A to D, the hop count is 2. Okay, so that's how A can send data to D, right? Now again, A doesn't know the path to D, the complete path to D. It just knows that in order to send data to D, it only needs to send the packet to C, and that's it, right? So this is a forward route entry. And then A will unicast the route reply to S. Okay, it's forward the route reply to S. Right, so so this is what we just said, create a route reply, right? The route reply contains the IP address of the source and the destination. Okay. If the route reply is sent back by D, the destination, it will contain the current sequence number of destination. Okay. Now, remember when we have the sequence number of the destination here, right? So assume this is the sequence number, let's say, we said before, let's say it could be 12, right? From C, it would be 12. Now, the current sequence number of destination may not be 12 anymore. It could be 20, right? Because from the time that C established the path to D, at that time, it was 12, right? But now many operations has been performed by the destination, many events have happened at the destination. So now the current sequence number of the destination is 20, for example. So the route reply will contain 20 here. Okay, it will contain 20 here, not 12 anymore. Okay, not 10 anymore. In the route request, remember we said we put 10 in here, but now at the destination, many events have happened. So now this becomes 20. So the destination will put 20 in here. Okay, and then the hop count would be 0. And then every node on the way back will increment the hop count by 1. Right? So when it reaches the source will have the correct hop count of the path. And then the lifetime of this route request, that means the lifetime, so that after some time, this route reply will be invalid. So to prevent the situation where we reuse obsolete route reply that circulate in the network for a long time from the past. Okay, so we have a lifetime here. Right, so this is by destination. Now, if the route reply is sent by intermediate node, basically by C in this example, right? Here, this is sent back by D, but in this case by C. All right, so this is the example we have here. Then it will store the destination sequence number, right? So we said it could be 12 here, it could be 12. Okay. So it could be 12 here. And then the hop count, the distance to the destination. So basically this will be 1, okay? And then the value is value of the lifetime, so the lifetime of the route reply here, okay? Right. So in AODV, they use the lifetime or the timer a lot so that we can throw away anything that have been in the network for quite some time and have become obsolete and may have become obsolete. Okay. Right. So, and then when an intermediate node receives the route reply, it set up a forward path entry to destination in the route table. Okay. So basically, so let's say in this example, when S received the route reply from A, it will make a forward route entry, okay? And basically forward because now the destination would be D and the next hop would be A, right? And the hop count would be 3, increment from A A would be 2 and it would be 3. All right, so the forward path entry contains the IP address of destination, IP address of the node from which the entry arrived, basically A in this case, right? And hop count to the destination. Okay, hop count to destination is 3. And then the lifetime again, when it's expired, we remove this entry from the cache or from the memory. Okay, so that we don't keep obsolete information, right? To obtain the distance to destination, a node increment its distance by 1. So we've seen this before, right? The destination started with hop count equal to 0, and every node received the route reply will increment this by 1. And if the route is not used within the lifetime, right? So this lifetime here, if within that amount of time, let's say within 5 minutes, and the route is not used, then it will be deleted from the routing table to save space, save memory. And after processing the route reply, the node forwards it to the source, toward the source, go back on the reverse path. Okay. All right, so Joshua has a question. How can the destination node send the route reply when route request ends as soon as the intermediate node is found? Okay, no, I mean, this is when we talk here. Okay, no, this is our two separate situation. What it means is either this or this. All right. Does that answer your question, Joshua? These two are not two consecutive events or actions. Either this is executed or this is executed, but not two the same, or not two one after another. Does that answer your question, Joshua? Yeah, I know why it can be confusing because of the way it's presented. Yeah, but this happened when sorry, 1 second. Sorry. Okay, so either this happened, the destination received the route request and it sent back the route reply, or an intermediate node C has a path to the destination and it will send back the route reply. Okay. Right. Okay, so this is what we see before. So yeah, so remember we said before, a route request may take several paths, right, to arrive at the destination. And because of that, there may be multiple route replies for a given destination from more than one neighbor. Okay, so you can imagine, let's say if we have another node E here, right, and then E has a path, and then let's say E and then F, and then F has a path to D, right? So B, E here, F here, and then from F we go to D. So if B has a path to D, so both B and C, they both have paths to D, so they can both reply. Okay, they will both reply because they know a path to D. Okay. So in that case, the nodes only forwards the first route reply it receives. What it means is A will receive 2 route replies, one from B and one from C. Whichever comes first, A will forward to S and ignore the other one, right? But if A receives from B first, right? And after that, A receives the route reply from C. Now, if the route reply from C has a larger event number than the route reply from B, okay, than the event number in the route reply from B. If this route reply has a larger event number. What it means is it's more up to date, right? The event happens after this. It's more up to date. Then in that case, A can forward this route reply from C to S as well. All right. So A received from B, forwarded to S, then receive another route reply from C. This route reply has a larger event number than the event number in B's reply. Then A will forward that to S as well. Okay. Or the second route reply has smaller hop count, right? So basically a smaller hop count means a shorter path, right? So you should choose a shorter path, right? So in that case, assume this path here is 1, 2, 3, 4, right? The hop count here is 1, 2, 3, sorry, 3, 1, 2, 3. So the hop count is 3 from B, E, F, D, right? It's 3. So A received a reply from B, forwards to F, but then receive a route reply from C. And the hop count is 2. So A also forwards that to S as well. Okay, right. So basically we choose a shorter path in this case. Okay. Otherwise, any future, if a route reply has a smaller destination event number or a larger hop count, then it could be discarded, okay, to reduce the number of messages in the network. And then the source can begin data transmission as soon as it receives the first route reply, right? As soon as it knows a path has been established, and it can send data immediately. Okay. Right. So, and for data delivery, it will use the forward route entry, right, in the routing table. So when it has the data to send, it will check the routing table. The destination is D. Then it knows that the next hop should be A. So it will send a unicast by unicast to A. Okay. And then when A receives the data packet, it checks its routing table. It has destination D. Next hop is C, so it will send to C. C receives it, checks the routing table. Destination D. Next hop D, so it's sent to D. Okay. All right. So, and this is one example, as we said before. So you can see here, this represents the broadcast, right, or the of the route request, right, transmission route request or broadcast of route request, and the blue arrows represent the reverse route entry, right? So E would have S as the destination, and next hop is S. Okay, similar for C and B, and then again, this represents the reverse route entry F would have destination S. Next hop is E, right? G would have destination S. Next hop is C. Okay, so this is the reverse route entry. So basically, they building a breadcrumb, right? They're building breadcrumbs so that the route reply can follow these breadcrumbs to get back to the source here. Same thing here. Okay, so D does not forward the request anymore because it's the destination. So it's sent back the route reply, and the route reply will take this path here. Okay. Right. So, and these red arrows represent the path taken by the route reply. Okay. And then every time a node receives a route reply, it will set up the forward route entry, right? So when J receives the route reply from D, it will have a routing table entry with destination D, next hop D. F would have an entry destination D, next hop J. E, destination D, next hop F, and then S, destination D, next hop E, right? So this represents the the link to the next node on the forward path. Okay. And the data will follow these links in the routing table, right? So S, the data packet from S, destination D has to forward to E. E receive the data packet, destination D has to forward to F. F, destination D has to forward to J. And J, destination D has to forward to D. Okay. So remember, the route, the path is not included in the packet header, all right? And that is the difference between DSR and AODV. Okay, so I think we'll take a break here. So again, another 5 minutes break. When we're back, we'll talk about the midterm test, and then we finish the AODV. So next would be some optimization and some optimization of AODV. Okay, so we'll be back at 4:22. Okay, so now 4:17, so we'll be back at 4:22. Okay. All right, so yeah, so let's continue the lecture. So let's talk about the midterm test first, and then we finish the AODV lecture. Okay. All right, so the test is on Friday, next Friday, not tomorrow. Oh, I forgot this to go over the plan for next week. So next week we'll continue TCP. Yeah, and then remember tomorrow is the lab with Lewin in the lab. If you need to use the router and the wireless cards for the second lab, okay, just to remind you, if you need help or you need to use the wireless card or the router for the lab, you have to go see Lewin in the lab. Okay, so so the midterm test will be at the same time as the lab next week. It will be 112 minutes, and it will be in the labs 1002 and 1004. Okay. All right. 1 second. And the material would be on the lecture notes from the beginning up to and including today's lecture. So basically everything up to AODV, right? But not next week lecture. So next week lecture will not be in the midterm test. And then now if you need more information, you can go into the textbook and or the papers that I posted on eClass. It will be labs 1 and 2 and the practice question. Okay. All right. So why did I post the practice questions? Because some students mentioned that there is a lot of material and they may not know what to study. So if you study, basically the practice questions are based on the lectures, most of the lectures. If you study those practice questions, you would get about 60 to 65% of the material. I would say, or maybe 60 to 70% of the material already. Okay, so at least you can have a focus of about 60 to 70% of what you have to study. And then the rest, you can spend more time on the lecture notes in the textbook. Okay. There's a question from Savage is going to, so yes, one of the TA will be available on Wednesday. Remember, Honda will be available on Wednesday, and he posted the time and also the Zoom link on eClass as well under course announcement. If you go back to one of your emails, you can get the time for Wednesday and the Zoom link as well. Okay. Right. So you're welcome. So the midterm test rule, again, it's a closed book test, no notebooks or cheat sheets. You'll be given blank paper for scrapbook, all right? So you don't need to print paper, but you need a photo ID, a health card, passport, York UID, pens and pencil. If you use pencil, it has to be a darkness of at least HB, right? At least HB or a bit darker 2B, okay? No question during the test unless you find an error in the test booklet, in the handout, in the question, okay? And the reason I say no question because of course we don't want close interactions between people during this time, and of course yeah, you cannot ask question publicly in the room, so that's why we try to avoid question, right? But unless you find an error, then yes, please report to us so we can fix the error for everyone. You may leave the classroom if you hand in the test booklet before 1:10, right? Otherwise, you must stay until 1:20 because during that 10 minutes, we want to make sure that everyone can finish the test without being disturbed. Okay. So the midterm will have both short answer question and long answer question as well. So if you take a look at the practice question, that kind of question you would expect on the midterm test, okay? Can you post these slides? Yes, I will post these slides on eClass. midterm review in the next class. Okay, so in the next class, I will, you can ask question. You can ask question about the midterm test. A review, I guess probably, let me see, what do we need to review? Yeah, I'll think about it. I'm not sure what to review. If you do the practice questions, basically that's a review already, okay? So I heard from the lab section during reading week that we can get access to laptops to install the lab programs into Linux. Would that be available tomorrow? I'm not sure. I'm not sure what you're talking about here, Joshua. I suggest you go to the lab tomorrow and talk to Luin. Okay. Yeah, whatever student were able to do during the reading week, in the lab during the reading week, you should be able to do tomorrow when you go to the lab to see Luin. Okay, go see Luin tomorrow, and then you should be able to do the same thing that student did during the reading week. Would there be any MCQ question? Yeah, there may or may not be MCQ question. It depends on how many other kind of question, like the written question. Okay, so I will. It depends on how many written question, and then we'll decide whether to have MCQ or not. Okay. So next week is the midterm, and limitedness work card available using extending the due date for the lab. Yeah, so let me talk to the TA, and then if the TA agrees, and then we'll extend the lab. Okay. Because the TA need to give may have to give another section. So I will talk to him, and then I'll get back to you, okay, about extending the lab. I think it should be okay with him, but I'll let you know, okay? All right, any question about the midterm test? Okay, great. So let's continue with AODV. So we'll try to finish AODV today, and then we're done for the midterm test material. Okay, so let me get back to okay, all right, so there's a question from Joshua. Will you post midterm practice question? They already posted a long time ago. Yeah. Yes. So question from that, basically essentially on the midterm review question, sure we're ready to take the midterm. I would say if you study the practice question, you would learn already about 60% of the course material from the practice question. Okay, I wouldn't say everything, but I would say about 60%. If you are able to answer or to solve the problems in the practice question, okay, maybe 60 to 70%, depending on how deep you understand the material in the practice question. All right, so now we'll talk about route discovery already. Now we'll talk about route maintenance, how to deal with link failures. Okay. All right, so in AODV, every node actively monitors their neighbors to make sure that their neighbors are active, right? The links are not broken. So a neighbor is considered active for a routing table, right? So let's say, remember before we have from C to D, right? So if D has a routing table, C has a routing table for D, then if D is active within this interval, right? Active route timeout, this is a value. and a packet was forwarded using that entry, then that means D is active. Okay, so if we use the previous example, but if nothing happened within this interval, that routing entry was not used for this amount of time, then D is not considered not active. Maybe it moves away, for example, or it fails, battery runs out, for example. Okay. If a sort node moves away, a new route discovery process is initiated. Okay, so that's for sure, because if sort moves, then it cannot reach any other nodes. It had to initiate a new route discovery process. If an intermediate node of the destination move, then the next hop link's break will cause a link failure. Okay, and routing table are updated to reflect the link failure. And all the active neighbors are informed by route error messages, just as before. Okay. So let's consider one example first. Let's say C does not receive anything from D, has not used a routing table entry for D for some amount of time, and it times out. So now C assumes that D has moved away. So in that case, this link is broken. So in that case, it will generate a route error message, all right? And it's sent back to the previous node, which is A, okay? And it will list the destination that are now unreachable. So in this case, only D, but maybe other nodes as well, because maybe C moves away, and then it's out of reach of every other neighbors. And then it sends this to the upstream neighbor, sent to A, okay? All right. All right, so and this route request is forwarded back to the source as well. And when a node receives a route error message, it will check and mark the route to destination as invalid. Okay, so for example, when A receives the route error message from C, so A would have an entry destination D, next hop C, right? So now A knows that that routing entry is no longer valid, so it will delete that routing entry because C just told A that C doesn't have a path to D. Okay, right. All right, and in order to mark this route entry as invalid, it will set the distance to infinitive, right? It does not remove the entry from the table yet, in case the route D and C moves into close proximity, and now they establish the link again. So it can use this. So it just mark as infinitive. And after a while, when the lifetime or the timer expires, this will be removed from the routing entry. Okay. And when a sort node receives a route error message, it will reinitiate a route discovery process as before. So basically, the route error messages are propagated from a node to the source, just as in DSR. And then the same thing in DSR, the source can initiate a new route discovery process. Okay. All right, so yeah, so this example we just saw, the node received the route error. Okay, so when A received the route error message, it checked whether C is the next hop. Yes, C is the next hop on the route to D. It will delete the route to D, right? So make the distance becomes infinitive, and will completely deletes later when that entry timers expire. And then it forwards the route error to S. Same thing here. S will check whether A is the next hop. Yes. So, and next hop to D. Yes. And it will delete this route by setting the distance to infinitive and reinitiate a route discovery process. Okay. All right, so now says something that we have to take care of during the process of generating route error messages. Okay. So we said before, if a node cannot forward a packet on a link because of, let's say the link is broken, so it will generate a route error message. Okay. So this is important. X will increment the destination sequence number for the cache at X, right? What does that mean? Because assume that the route entry for D, right? So let's say assume in this example, the route entry for the SC is 12. Okay, so let's assume this is 12 at the moment. That means this route was established as event number 12, right? Now, when this link is broken, this is an event, and this event happens after the route was built. So that means this event now must be 13, right? It cannot be 12, it cannot be 11, it has to be 13 because the link broken at event number 13 after this route was built, okay? So that's why X increment the destination event number for D, okay? And then this new sequence number or event number is put in the route error, all right? So basically, C will tell everyone that I had a path, a route to D as event number 12. Now there's an error. The error happens after that. That's why the event number now has to be 13. Okay, so it put 13 in the route error. Okay, so that everyone knows that this is a new event. A path with event number 12 now becomes obsolete or invalid because this is a new event. And the event is the link is broken. So when S receives the route error, it will initiate a new discovery process for D, right? And now the destination sequence number must be at least as large as N, okay? So that means that the new destination sequence number for the route request, for the new route request, must be at least 13, okay? Must be at least 13, all right? Now it could be more than 13. Let's say between the time when the route was built until S received the route error message, it may have other operations, other activities. And now its sequence number becomes 15, right? S sequence number becomes 15. So the act or the event of generating a new request would become 16, right? It becomes 16. Then yes, S can use 16 here for the new route request, okay? But if S doesn't do anything, since it received the destination sequence number 12 from C, then now it can use 13 in the new route request, okay? All right, so again, we use these event number to make sure that we have a timeline of ordered event to select the most up-to-date activities or information, right? Oh, I just saw a message from Sanya. The midterm review question do not include ESR, LDV, or ad hoc network question. Can you add some question to this topic as well? Yes, I will try to find some question and I'll post them later. Yes. Okay. Probably this weekend. Okay, so let me write down. Okay, all right, so all right, and then so S will initiate a new route discovery process, put a new destination event number in the route request, and then when D receives the route request with destination number, let's say 13 in this case, right? So D will set its sequence number to 13, right? Now assume S set this to 16, as we said before, 16, because S may have some other events in the past. So when D receive the route request with number 16, then it will set its sequence number to 16, right? Unless D already had other activities as well, and now its event number is greater than 16. So let's say now D has an event number 20, okay? Then it will put 20 in the route reply, okay? It will put 20 in the route reply. And then everyone else see this route reply had to update the destination event number in the routing table to 20, because that's the current event that the had, which is to generate a route reply, right? So the route reply has event number 20, okay? Right. All right, so, and the last topic is to maintain local connectivity using hello messages. So in AODV, neighboring nodes periodically exchange hello messages to make sure that the neighbor is still alive and well, okay? So, and the absence of hello messages is an indication of link failures. So that means if a node doesn't hear from a neighbor, let's say for an amount of time, so the timer expires and the node can assume that the neighbor has moved away or the neighbor has died because of the battery, because the battery died, for example, right? So that's how AODV keep tracks of neighbors to make sure that to detect link failures periodically. So another way to detect failure is the absence of MAC level acknowledgement. All right. So remember when we learned about AO 2.11 medium access control, every transmission would have RTS and then CTS and then data and acknowledgement, right? If that acknowledgement doesn't arrive in time, right? So that means the node assume that this neighbor has moved away or fails or battery has died, for example. Okay, so that's an indication of link failures. All right, so now we talk about an example how event numbers or sequence numbers can be used in ODV to prevent loops, okay, to prevent routing loops, okay. So it's important in routing, in network routing, you don't want loops, right? So loops is the #1 enemy of routing in the network, okay? So loops is the #1 enemy of routing in the network, and we have to prevent loops to make sure that packets don't circulate forever in the network. Okay? So we've seen example of using sequence number to avoid obsolete routes, right? We've seen that before. We always choose a route or a message with a larger sequence number, okay? And by doing that, we can select routes which are newer, right, or more up to date, okay? So now now we consider one example how sequence numbers can help us prevent loops, okay? All right, so now assume that A has a route to D, right? So basically A sent a route request, it goes to B, C, D, and D sends back a route reply, right? So now, okay, now assume that, okay, so in this example, we don't use sequence number, right? We don't use sequence number. So that's the assumption. We don't use sequence number, and we see if we don't use sequence number, how can a loop is formed, okay? So assume that this link is broken, right? And then C sends back a route error to A, right? C sends back a route error to A. Sorry, just 1 second. Let me see. I think there must be another slide before this one. Okay, so I think we should talk here about this word. We'll go to the as a sample. Sorry. Yeah, sorry, I don't have the PowerPoint slides because if I had the slide, I can rearrange them into correct order. Okay, so in AODB, one optimization is to use local repairs. Okay, so the local repairs mean a link break should be repaired locally instead of notifying the source. Okay, so what it means is if in this case, let me go back to this example, right? So assume that this link is broken. Of course, C will send, before C sends an error message back to S or A, C will try to initiate a route discovery process to D itself, right? So basically C trying to fix a problem here without telling S or A. So C will initiate a route discovery process so that it can find a path to D, right? Now, if it's successful in finding a path to D, then it will update its routing entry without telling anyone, right? So basically now S doesn't know anything about this link break. A doesn't know anything about this link break. They will forward or send packets as usual. Only when the packet arrives at C, C will use the new route to forward to D. Okay, so you see in that way, we don't have to send route error messages. S doesn't have to initiate a new route request or route discovery process. So we can save a lot of network bandwidth by doing local repairs, right? Okay, so that's the main idea. Local repairs mean C will try to fix this link, this problem, if it can. Okay. Right. So let me see here. All right. Okay. So that's what C would do, try to fix the problem, and it will use a small time to live, basically a small hop count. Because the destination probably hasn't moved too far yet, right? It's moved, but maybe just still very close to C. So it doesn't have to use a large time to live or hop count. And then if the first repair attempt is unsuccessful, then it will send a route error message to the source. Okay, so it tried, right? But it failed. Yes, now it had to tell the source to find a new path, a new route. So the advantage of local repairs is that the links can be repaired with less overhead because we don't have to send route error. The sorters have to send route requests to the whole network. So we can have a lower overhead, lower delay, and lower packet losses, right? But the disadvantage is if C cannot find a path to D, then you would have some delay there, right? Because when C tried to find a path, there's some delay. And there may be packet losses as well, because packets will arrive at C and then C have to buffer. But if it doesn't have enough buffer, then it may drop those packets, right? Yes, it has to drop those packets. So in that case, we may have longer delay and higher packet loss if C cannot find a path to D, right? So the advantage, but disadvantage as well. Okay, so now we know about local repairs. So we go back to the example here to show if we don't use sequence numbers, we may have a loop. Okay. All right. So we said before A has a route to D, right? And then this link is broken. And then C. And then A doesn't know anything about this link is broken because the route error sent by C is lost. Or remember we said before, C doesn't even send a route error, right? C doesn't even send a route error because it's trying to fix the problem locally. So now C will perform a route discovery for D. Okay. So C will broadcast a route request. Now, and then the route request will arrive at B, right? Remember, this is broadcasting. And then B again, broadcast a route request to A, right? So now A received the route request, let's say, but let's assume it's received a route request through this path here, C, E, and A, right? Remember, because this route request can reach B and E as well. And then E will send the route request first to A. So when A received the route request, A thinks, oh, I received a route request from E, and I know a route to D, BRB, right? So A will send a reply, and the reply saying that I have a route to D, A, B, C, and D, right? So you can see that now the route reply will go A, B, C, and then E, right? So now we form a loop here. We have a loop here, okay? Because it will C, E, A, B, C. So now we form a loop because the route request will go C, E, A, right? And then A will put C, E, A, and then B, C in, that will be considered as a route from C to D, right? So you can see we would have a loop in this case, all right? Now, yeah, we have a loop in this case. But, and in this case, because we don't use sequence number, okay? Now, if we use sequence number, so remember the route from A, B, C, D before, this route here, it has sequence number 12, right? We just give the random number like 12, it's number 12. So when C generates a new route request for D, it cannot use number 12 again, right? Because number 12 was a past event. So now it has to use a higher number, right? So let's say it's use number 13. So the route request from C will carry number 13. So 13 will arrive here, 13 arrive here. So when A received the new route request, number 13, it checked its routing table. Yes, it has a path to D, but this path has number 12. All right, this path has number 12. And remember, if it has a path with a lower sequence number, it cannot reply, right? So in this case, A cannot reply because the path it has event number 12. The new route request has event number 13. So that's why A will not reply. And by not replying, it will not form a loop, okay? It will not form a loop. And that's how we use sequence numbers or event numbers to avoid loops in this case, okay? Right. Okay, so some optimizations for AODV. So one optimization is to send with a small time to live field, right? Remember we said before we send with 0, so we can reach the 1 hop neighbors. If we cannot, then we increase it to 2 to reach 1 hop, 2 hop, 3 hop neighbors, right? And then to 4 and then to 6. So that way, if no route reply when we use a time to live equal to 0, then we try a larger like 2, and then if 2 is not successful, then we try 4, for example, right? And as we said before, the advantage is we minimize the amount of traffic in the network, but the disadvantage is the delay of establishing a path may be longer because we have to keep trying with 0 and then 2 and then 4, right? Yeah, so and this is the main idea we just talked about. It's called expanding ring search. Okay, expanding ring search. And we say ring because we have a source and we reach 1 hop neighbors, right, around a ring. And then we reach on 3 hops neighbors, right? So again, the advantage is less overhead when successful, but longer delay if route not found immediately. We have to go to the next ring, right? 3 hops and then 5 hops, for example. Okay, and we already talked about local repairs, right? So this is a compare with AODV, sorry, DSR. So compare with DSR, routes doesn't have to be included in the packet headers. Okay, so that way we can save the bandwidth, because the larger the packet, the longer it takes to transmit, right? Nodes in AODB maintain routing table, and it contains only entries that are active, right? DSR doesn't have routing tables. They just put the whole path, the whole route in the packet header. And at most one next hop per destination. Okay, so in the routing table, we have an entry for destination and then one next hop. DSR may contain several routes to a single destination. Remember, every time it hears some route, it just keeps caching and caching, right? So in that sense, it may have several routes to a single destination. So this may waste memory, right? Consume memory. Unused routes expire even if topology does not change, right? Remember, we have a lifetime field for each routing entry. So if that route is not used and it expires, so we remove it from memory to save the memory in because mobile devices have limited memory capacity. And it's reactive or on demand. We only build a route when and loop should route discovery process from and use update. Okay. So that's the end of AOD, and that's also part of the TOTOM test as well. Okay. So the lecture officially ends here. Thank you everyone for attending the lecture. So I will stay for the next 5 or 10 minutes in case you have questions, right? So otherwise, have a nice evening. I'll see you next week. Okay. Oh, I have office hours tomorrow from 1 to 1:45 if you want to see me tomorrow. Okay. Nice evening, everyone. No, it's a different link for office hours. I think it's on eClass. Let me show. It's on eClass. So yeah, I mean, yeah, it's on eClass, right? Right. Yes. But if you exactly right, exactly. So that could be, that could be, how can I say? I could say a redundant question, right? Because by then you should have studied for the midterm test, right? Yeah. Yeah, exactly. Yeah, I'm not sure how, when you say intensive, what do you mean by intensive? Like you have to do no, I wouldn't say too much math. Whatever math formulas that we have in the lecture notes, that would be the math, right? Let's say to compute the antenna height, right? To compute path loss, whatever math we have in the lecture notes, that would be. You're very welcome. Very welcome.